On checking the mic volume. Why don't we begin? All right, welcome everyone to the 24th Greenstein lecture. This year's Greenstein lecture is Chris Kochanek. I'll introduce Chris in a moment, but first I want to take a minute to remember the person for whom this lecture is named. Jesse Greenstein was a pioneering astronomer who was renowned for contributions to quasars, white dwarfs, an understanding of stellar composition, among other areas. He was one of these wunderkinds who started college at age 16 at Harvard, completed his bachelor's degree in 1929, master's in 1930. In the depths of the Great Depression, he actually dropped out for some time, helped the family business recover, returned, received his PhD in astrophysics in 1937, and he soon moved to Yerkes Observatory and not long after joined the faculty at the University of Chicago. In 1948, a date that many Caltech astronomers will remember, Greenstein moved to Caltech and founded our department. This included the development of a new graduate program in optical astronomy, and it was in conjunction with the dedication and first light of the 200-inch telescope, Palomar Observatory. Greenstein stayed at Caltech for 24 years and built the program into the world-leading department that we have here today. In 1955, Greenstein also took up radio astronomy. This was a brand new field at that time, sort of arising out of the Second World War period, and played an important role in developing NRAO nationally and the Owens Valley Radio Observatory locally. He also chaired the 1970 Decadal Review on Astronomy. Greenstein's scientific legacy includes important research with Maartin Schmidt on quasars, spectroscopy of white dwarfs, and he observed over 1,000 nights personally at Caltech's major facilities, especially the 200-inch at Palomar. He was honored with many achievements, and these included an election to the National Academy of Sciences and the gold medal from the Royal Astronomical Society. So that's our forebear, Jesse Greenstein. This year's Greenstein lecturer is Chris Kochanek. Chris is a professor at The Ohio State University and has the impressive title of Ohio Eminent Scholar. Chris did his undergraduate work at Cornell and received his PhD here at the physics department in 1989. He's a recipient of the Beatrice Tinsley Prize, the Danny Heinemann Prize, among others. Chris has worked on a wide variety of astrophysical topics that include binary neutron star mergers, the mass of the Milky Way, the cosmic distance ladder, luminosity functions of galaxies, as well as using gravitational lensing as a tool to understand dark matter and dark energy. Chris is also especially interested in time domain astronomy. I think that's a bit of what we're going to hear about today. This includes explorations of variability properties of massive stars and quasars, as well as supernovae. Much of this work is through a survey called ASSASSIN, a network of small telescopes that Chris co-built and co-developed. According to ADS, the ASSASSIN survey now has 132 papers, so it's quite good. Please join me in welcoming Chris here to visit.
The best part is when the move to Ohio first appeared on the job rumor page, it was as the Eminent Scholar. Unfortunately, it didn't stick. So since it was the Greenstein lecture, and I sort of knew what Jesse worked on, I met him briefly when I was a graduate student. We didn't interact much. There were some possibilities about what to talk about, and really the only one that overlapped was AGN, so I thought I'd talk about AGN. And of course, one of the things he was famous for was some of the first determinations of the redshifts of AGN, in particular 3C273. And so I will hit 3 Caltech faculty on slide 1. But I will point out that 3C273 is greatly faded from its former days of glory. That it's now about 3 times fainter than it was at the time of those observations. So I'll talk most extensively about the normal variability of AGN and things you can do with it. And then over the last 10 odd years, the realization of many other forms of AGN variability, which are whatever, abnormal. And so we'll do a little tourism of abnormal AGN variability. So it was realized almost immediately that all AGN and quasars burbled along with some random variability at the level of a round number, sort of a tenth of magnitude on time scales of a month or so. And so here's another example. It's some local Seyfert galaxy, and there it is bumping up and down. And for a long time, no one really had anything to do with these things. First of all, because the data wasn't really available, right? Doing surveys of time domain things of large enough objects to be interesting was super painful, both because the instruments didn't really exist and because of it's my night on the telescope and I'm damn well not going to do your observation, spirit of using optical telescopes. And that started to change a lot. Initially, the biggest one that really did it was less so for extragalactic things, but the Ogle survey actually provided some of the best initial light curves of quasars. Then also the SDSR survey, which provided not so great light curves of many, many more quasars. But now with the advent of the modern time domain surveys like CTF, PTF, RS-ACID, and so forth, you have much better light curves of many things. It was proposed by Kelly and company that a way to characterize these variabilities was to describe them with a stochastic process, in particular one called a damped random walk, which is exactly what it says it is. If you do a random walk, you steadily move away from your point of starting, square root of the number of steps. But clearly quasars don't do that, so you need something that will limit the growth, and so you put in a damping term. And so it's a stochastic process with two parameters, a time scale on which you try to return to the mean, and an amplitude by which you try to vary. And the amplitude is basically the difference in magnitude you would get by 2 points separated by infinite time. Okay, so it's nice and simple, two parameters. If you're into structure functions, which some astronomers are, you can ask what is the mean square difference on average between 2 points on a light curve separated by some amount of time. And it has this structure. It basically goes to 0 and 0. It rises as a power law, and then it saturates. So short time scales, if I go and look at the quasar a millisecond later, I will get the same magnitude. If I go and look at it on time scales much longer than the damping time scale, it will asymptote to this asymptotic amplitude. Good. So it's nice and simple, two parameters. Is it any good? It's okay. It is super fast. As compared to many Gaussian processes, you can use it both to generate things and to model things. It takes only order n operations to do anything, whereas if you make most other choices, that becomes n cubed. If you do a Kepler light curve where n is 50,000, there is a difference between these two scalings. And just to give you a sense of here's how you generate a damped random walk light curve. You pick a Gaussian random number with an amplitude of your sigma. That's your first point. And then you get every other point by just applying this. You take your previous number, damp it, and then you add a Gaussian random deviate whose amplitude depends on how big a step you're taking. If it's a tiny step, you don't add very much. If it's a really big step, you add basically sigma again. If you'll agree that you could probably implement that in about 30 seconds. If it's in Python, it will work today, but it won't work tomorrow. But it's really fast. Okay. And then you have to add in a mean. Right? It doesn't say anything about what mean to add. Okay. If you take those parameters, what makes them of some interest is that they do correlate with other properties of the quasar. A lot of these are not super good because, for example, if we look at the time scale, you actually need a very long light curve, like 10 times tau, in order to get a reasonable estimate of tau. Okay, but here's an example. These are all black hole masses, which are locally calibrated. They're like dynamical reverberation mapping masses. These are the tau. And you can see that the black hole mass scales with tau. The scatter doesn't look bad, but the scatter is actually just as good as every scaling of parameters with black hole mass, except with the Blazars dispersion. Okay. The problem of you needing a long light curve means that to really industrially apply this to large numbers of quasars, you need something that goes deep and will last for 10 years. And in theory, that's starting up now. So LSST will be the thing that can really do this quite industrially. But you have to wait like 5 years. Okay, is it right? No, it's certainly wrong in detail. Empirically, using Kepler light curves and some things we could do with the Ogle light curves, it is almost certain that it cuts off more sharply on short time scales. This is a model overestimates the amount of variability if you go for very small steps. Physically, I can give you a reason why that has to be true, is what the damped random walk is. It is really a solution to what's called a stochastic differential equation. What that means is it's a differential equation driven by something that is random instead of something which is some function you're used to writing down. Okay, and so the DRW is you have the differential equation, which is just an equation for an exponential. And then the driving term is white noise. Okay, and if you go through all the calculations of this, you will find that you will get that structure function. All right, but that means that if I give you one of these damped random walk light curves and take its derivative, part of its derivative is white noise, which is not a smooth function. Okay, I'm pretty sure that the actual equations that govern an accretion disk are a bunch of PDEs consisting entirely of smooth functions, and so that the derivative of an actual quasar light curve cannot be something like white noise. And so on short time scales, there has to be some sort of a cutoff. And unfortunately, it is really, really difficult to impossible to probe this. So Kepler could do a little of it. TESS has too many idiosyncrasies. It's just very, very hard to try to do the analysis for whether it's a break on short time scales using TESS data. And ground-based data, as you go to these short time scales, we never get the cadence and we don't have the small. So at the moment, this is, as an experimental thing, too hard to really probe. But it's there. Okay, another little interesting philosophical question is whether quasar variability is Markov. So what Markov means is that my next state depends only on my current state. And you can see that in this equation for how to evolve your damped random walk. Is all I need to know is how bright I am now. I don't need to know anything about how bright I was from whatever I equals 1 to I equals I minus 1. What happens next depends only on where I am. Okay. And so sometimes you would ask as well, is that are quasar light curves really Markov in this sense, that what I do next, there's really no predictive power from knowing what happened before. In some sense, if we go to the question of what the underlying equations are, if there are a bunch of PDEs, in some sense, it actually is Markov. That if I gave you the full state of the accretion disk now, okay, I could do the future evolution without any reference to the prior state. But that's giving you the full, whatever, n-dimensional state of the accretion disk. Whereas here, I'm just giving you a number on a light curve, which presumably does not encompass all of that information. It turns out it's surprisingly subtle to actually test it, because there's a subtle distinction between, is it Markov in the sense that I can predict, I don't get any information from my prior light curve to predict the next one, versus the fact that I will get a better parameter estimation of how to do that prediction by modeling the full light curve. So I will get a better estimate of the mean, sigma, and tau by modeling the full light curve. And so if I don't very carefully separate parameter estimation from testing Markov, it becomes something you're not doing a test of anymore. And so it's actually very tricky to answer this question. I've tried playing with it, and I haven't really gotten anywhere. It's an interesting little philosophical question. Okay, so we can model the accretion disks. It's good for a bunch of things. It gives you some numbers you can correlate. By the way, should I say those numbers correlate with black hole mass, Eddington ratio, wavelengths, all the things you might think they correlate with. However, you're then kind of stuck at the moment because we don't really have a way of then connecting those scalings to zero. Okay? So it's interesting empirical. It may have empirical uses, like as a way of estimating black hole masses, but we don't have that connection for how to go from there to things you might care about accretion. All right, so the next thing you might try to use this variability for is to estimate the sizes of accretion disks. Okay, that seems like a pretty important test. What does size mean in the context of accretion disks? Since obviously it's a continuum structure. The basic scheme is if we stick to thin disks, in a thin disk, the temperature drops as r to the minus 3/4. The characteristic wavelength of the radiation emitted at some temperature is going as 1 over the temperature. So that says you expect the size scale you're looking at to scale as wavelengths of 4/3. Okay, so what you're really looking for is you're going to make some estimate of the size. Okay, they'll give you a scale that corresponds to some radius of the accretion disk due to the temperature. And then you can further ask, is that the right size given the properties of the thin disk model, for example, and does it scale with wavelength as you expect? So, there are two ways of doing this. One is to use microlensing and gravitationally lensed quasars. There you are not using the intrinsic variability of the quasar. And the other is to do what's called continuum reverberation mapping, where you do comparisons between light curves at different wavelengths. So let's look at the first one first. So there's a lensed quasar, an HST image of a lensed quasar, a Huckver's lens. Although we did really fight calling it that because it was fine to give cutesy names to lenses when you had 4 of them. As you have hundreds, cutesy names become a burden. Anyway, so it's also Q2237 plus L305. If you don't know, this one was actually found in the CFA redshift survey. They took a redshift of a redshift 0.03 galaxy and discovered it was at redshift 1.6, and discovered that in fact there were 4 images of a quasar hiding in the bulk of this galaxy. So the overall potential of the galaxy produces this big splitting of an arc second or so. All of the stars behind that image also produce magnification of the lens. In fact, if you could take an image of that image at microarc second resolution, it would break up into a whole bunch of blobs created by the stars near the image, converting it into multiple images. And what you get is that the source is really crossing a magnification pattern like this, created by how the bending of each of those individual stars focuses or defocuses the rays passing by. Okay? The planetary people do this in the really simple limit. They do it where you have 2 objects, 1 object. Here it's the entire field of stars that are doing it. It's like microlensing with planets, but where you're optically thick instead of optically thin. Okay? So here are 2 patterns. Then to add the fun, okay, so 2 things are moving. First, the lens, the source, and us are moving relative to one another. So there's a mean velocity across this. But then all the stars are moving too. So it's not a static pattern. And so here are 2 movies. This is a small source, and it will produce the light curve up there. And the rule is whenever you cross one of these sharp edges, strictly speaking, right on the edge, the magnification is infinite. Okay? And then it's regularized by the size of the source. So compact source, higher amplitude variability, less compact source, less. Okay, so I think this activates that. This was done by a student who went rogue on me. He said, don't do this project. You need to finish your thesis. And he went off and did the moving stars anyway. Got that Sean Poindexter. And so you can see is you're getting these kind of fairly jagged crossings. Nothing happens in the valley. Some of these little scooters are actually moving faster than the speed of their patterns. They're not something physical. So the motions of the magnification patterns can be much, much faster than the motions of any of the actual stars. Okay. And then you can see what happens when you have a big source, which just averages over a lot more. And not surprisingly, if you average over a lot more, you get a lot less variability. All right, so the game is you take one of these quasars, you monitor it, you have to get light curves of all of the images, you have to work out the time delays, you shift everyone by the time delays, take magnitude differences, that removes the intrinsic variability, and what's left is the difference in the microlensing variability between 2 images. The amplitude of that then depends on the size of the source. Okay, so believe it or not, what we do is we take those actual light curves, we produce a bunch of these patterns, and we randomly draw light curves from the patterns as a function of source size. You do this a lot of times. And you can actually come up with things that go through the data. We do it a lot of times. And that lets you get a probability distribution for which sizes you can get. Because obviously, if I use something which was too small, it would be too peaky. If it was something too big, it would be too shallow. So you could get a size estimate. Okay. So here's basically what you get. Let's focus on the expected scaling with black hole mass, which in thin disk theory at fixed Eddington ratio, so that's this term, would go as mass of the black hole to the 2/3 power. So here is mass of black hole, basically done from broad line width, basically poor man's reverberation mapping results. Here is the size of the disk. Here are the results. Fit. And instead of 2/3, you get 0.8 plus or minus 0.17, which is not bad. The mystery, though, is if you ask, here's the slope. Okay, you got that slope. You should have gotten this slope, but okay, those are the error contours. It's all good. You also get basically a size at that scale, mass scale, and you get this size. And from what we think we know about Eddington ratios, you should have gotten that size. And so the size scale you get out of this is the disks are in round numbers twice as big as you expected from theory, given what you think the Eddington ratios are. Right? All right. After doing a bunch of these, we gave up. Right? But basically, at the time, there was no way to do this 10 times better. My general feeling is I can't do something order of magnitude 10 times better. It's time to do something else. I didn't want to spend 10 years doing it twice as good. So it's sort of stuck. This would change again with the advent of Rubin, where Rubin would automatically get these light curves. You will need like 5 years. All right, let's see. Maybe there's some other way we can do this. So this is called continuum reverberation mapping, and this is mainly only started more recently. And so the basic idea is, here's my black hole, here's some disk. I have some sort of variable radiation from a central source. Okay, the buzzwords are usually people talk about it being the X-ray corona. You can actually show from microlensing of X-rays that the X-ray corona is very compact, much more compact than the optical emission. And so if this varies, and you imagine it illuminating the disk, okay, it will go out, heat the disk, and drive temperature fluctuations. Okay? But the time scale for when you see it is shorter for this guy than for this guy, because there's extra path length here than from here. And these paths are actually the same for an observer. Okay, it's called the lamppost model. Imagine a central variable lamppost. To me, it can't really be the X-rays, because having the X-rays drive the disk is the tail wagging the dog. X-rays are not. So I would say it's something about the inner regions of the accretion disk. You also see in some of these that the optical variability completely decouples from the. Again, suggests it can't really be driven. Okay, so now you get an estimate of the size because you should see a delay that is basically scaling with the distance you are from the center divided by the speed of light. It's just a light propagation effect. Okay, lag between bands, which is scaling as the wavelength of the band. Okay, you can do this with less spectacular light curves, but here are the 2 most spectacular sets of light curves of AGN. These are the AGN Storm 1 and 2 collaborations. And it's probably a little bit small, but that's 1180 angstroms, and that's a Z-band. So both of these represent some 150 orbits of HST time to do UV spectroscopy. Has lots of other uses. Okay, but now the game is I pick one of these light curves or multiple of these light curves. I find out how I have to shift them to match them to the other light curves, and so I can get differential delays as a function. All right, here's the results for 5548. Okay, so it was referenced relative to a swift light curve, so that's why 0 has a finite wavelength. And then here are the lags as a function of wavelengths. This curve under here, one here is lambda to the 4/3. The lag is scaling very nicely, is what you would expect for this in this theory. The best fit is you never, it's a little bit off, but it's consistent. Only problem is you ended up with the same issue, is that the Eddington ratio you would infer from the luminosity of the quasar differs from the Eddington ratio you would infer from the scale of the lags, again, by this factor of 2. And so both of these methods generally find that disks are about disks have a temperature scaling basically consistent with thin disk theory. So temperature going is r to the minus 3/4, but the disks are bigger. The currently popular explanation, which I'm not super keen on, is basically to make a lot of what you think is continuum emission from the disk pseudo-continuum emission from the broadline region on larger scales. Basically, you just dilute it. Two things bother me about this. First is when they try to model this, it predicts there should be a big Balmer jump in the spectrum. There is no big Balmer jump in the spectrum. The second thing is the broadline region doesn't know anything about producing lambda to the 4/3, because you're doing this by some completely different thing unrelated to the temperature profile of the disk. So why would it produce the temperature profile? But anyway, it's a way you can do this, and you can do this for some number of things. But okay, the lamppost model is kind of weird. It's like, why would variability in a quasar be dominated by central variability from something? If you go and look at someone's simulation of a disk, it's a train wreck. The disk is doing all sorts of rubbish all over the place. And some of that ought to be converted into variability. So in fact, you would expect variability intrinsic to the disk and not driven centrally. So let's try the following game. Let's assume the disk is axisymmetric. Okay, yes, it's not axisymmetric. But unfortunately, there's this little problem that we're going to take two-dimensional data, and you can't really convert two-dimensional data into three-dimensional data. Well, you can, but I can also give you whatever you want. So by making axisymmetric, you're really just taking two-dimensional data and putting it into two-dimensional data. So that mapping I can do. I can take what temperature fluctuations do I need in the disk as a function of time to produce the light curves I see. Okay, so it's just a mapping problem, an inversion problem. You do have to like linear algebra. You have to like some really big matrices, like 50 or 100,000 square. But you can do this mapping. These sorts of mappings tend to have places where they are unstable. Basically, you're doing a big matrix inverse, and the matrix is not well posed. It's near singular in various places. So you have to do something about smoothing. And so you put in a smoothing parameter, which we call C, and basically small values of C means we're not smoothing it very much. Big values we're smoothing a lot, and we'll just have to evaluate how well we're doing. So an important thing to appreciate about disks and how they produce fluctuations at a given wavelength is that the kernels of that transfer are super broad. And it's not the thickness of the filter. It's not the filter width. It's the black body function. So these are for a bunch of the ones where we could do this. Here is the log of the radius. And then here are the transfer functions associated with various filters. So blue filters on the left, red filters on the right. So this is 5548. Showing you one of the light curves. And so that's HST at 1,000 angstroms, and that's Z band. And you can see, even with that big a wavelength separation, they're just barely beginning to be completely independent probes of the disk. Again, this is not the filter, it's the black body function. And that's one reason why you need to do the smoothing is all of these filters nicely broke up and were decoupled, right? Then this would be a much more stable problem. But because they overlap so much, you have more stability problems. And you can see this is true for all of them. And you can see there's a spectrum. So there are these ones, this was AGN Storm. And then there are a bunch where there was Swift data. There was some programs doing a lot of intensive monitoring of Swift. There's some where it's Swift and optical. LSST will be able to do things similar to Swift, but at longer wavelengths, so basically shifted outwards. Okay, test problems. So basically what we're producing is a kind of space-time diagram turned on its side. Here's time, and here is log radius in units of the inner edge of the disk. So 0 is the inner edge of the disk, 10 times the inner edge, 100 times 1,000 times. So in this kind of a diagram, the lamppost model is a signal moving outwards at the speed of light. So if we just put in a sinusoid of some randomly chosen amplitude, but it's not randomly chosen, it's kind of sort of right. Here is an input. We take that, we sample it like the light curves of the data, add noise like the light curves of the data, reconstruct as a function of smoothing, and here are the sorts of things you would get. And you see what I've advertised, right? At very low smoothing, you get lots of fake structure. Okay, as you smooth more and more, it gets closer, but you start to wash things out a little bit. Here's the sort of thing you might expect for intrinsic variability in the disk. So we put in a basically slowly moving incoming wave. Why is it slowly moving? Well, you can see the speed of light is basically nearly vertical. If I make the slope much flatter than nearly vertical, that means it's slower than the speed of light. Okay, ingoing because it's going this way instead of that. Okay, and you play the same game. Right? So basically, it gives you a feel for what's going on. All right. So here are results for 5548 in 2 dimensions. This is more smoothing. This is sort of an experiment of increasing the resolution of basically making the matrices bigger, more zones in the disk. So if you smooth it a lot, you get something that looks pretty lampposty, but not perfectly. But if you go anywhere in between, you can see there are also patterns that seem to be some kind of slowly in-moving and out-moving wave pattern. And this is true of all of the ones we did. Oh, by the way, these models then fit the light curves perfectly. So that's one of the best models. It just goes through all of the light curves. We get this for all of the kind of 10 objects we've done. That all of the ones at kind of the intermediate smoothing that seem to be good for the test problems show mixtures of things that look lampposty and things that don't look lampposty. If you look at the light curves, you have the impression that the lampposty signal dominates. Right? And so why is that happening? Let's go back to this. Remember the broadness of those kernels. So if you imagine a really broad kernel on here, right, it's basically moving along this stripe. If I imagine a really broad kernel on here, it's averaging over stripes. And so what happens is if you have that broad black body kernel, it tends to average out slowly moving waves. Okay? And so even if in these reconstructions, right, it's kind of giving semi-equal temperature amplitudes to the ingoing slow waves and the outgoing lamppost signals. And what you see in the light curves, it would look like the lamppost dominates. Our prediction, though, is that as you look at longer and longer timescale waves, basically you're going to look at things with longer and longer wavelengths. As you look at things with longer and longer wavelengths, they're going to be less and less well averaged out by the blackbody kernel. And so the expectation is these light curves are all fairly short, right? Because no one's going to give you 10 years of HST time to do this. Well, they could. Well, probably not anymore. But if you have a really long time scale, our expectation is as you go to longer and longer light curves, you'll see more and more signal corresponding to this slower moving uncorrelated variability. There's actually something else which is a good thing to pursue with Rubin, because it will both provide the multicolored light curves and the long time scale. There is some evidence of this in the light curves you have, that there are more uncorrelated long-term variations in light systems. But it's kind of like, you think about a sine wave, you've kind of got like half a wave of the entire. Okay. What about the anomalous variability? So the first one that came to whatever observational prominence are tidal disruption events. So this is where you take a star, run it close to a supermassive black hole. The tides of the black hole shred the star, and to 0th order, if you completely shred the star, half the mass of the star is bound and will be accreted, or can be accreted, I should say. and half of the mass of the star goes flying out. The first people to actually get the energetics correct were, I believe, that Lacey paper. The previous papers had the debris being distributed in energy by the binding energy of the star. It's actually distributed in energy by the geometric mean of the orbital energy and the binding energy of the star. So that gives you a much higher velocity. So I believe they were the first to get it correct. There's some early papers by Rees and Ruffini. And one of these was in my thesis. So that just was. Their first arguments were for detections in archival X-ray data. I never found these very satisfying because basically what they would do is in archival X-ray data, they would find a single flare. You had 1 point or 2 points, no ability to get follow-up data, maybe. Okay. Optical UV really started about 10 years ago. There was some archival work by Svort, Van Velzen. There was a discovery by Senko, Gazari, and retrospectively, if we would say is we realized that many of the optical surveys, time domain optical surveys, were simply avoiding the centers of galaxies. But if you're thinking about it, if you're just looking for supernova, there are a lot of good reasons to avoid the centers of galaxies. They produce false positives. They waste your spectroscopic resources, which you could have spent on supernovae. When we started Assassin, didn't really have any choice. We have a 16 arc second full width half max. So basically, that central pixel is the galaxy. So if we threw that out, this would be a very short survey. And so we quickly started finding a number of quite bright TDEs. The bias against centrals of galaxies has gone away. And there are now some 100 optically selected TDEs. As the blast from the past, the first simulation of a TDE with smooth particle hydrodynamics, the lofty total of 40,000 particles. Run on a Cray XMP, which no one even recognizes the name of, or at least no one of junior age. And the scale here is that is the size of the horizon. The star is magnified by a factor of 15, so you can see. TDEs are creatures of the ultraviolet. And so with Swift, I was at the Swift 20 years of Swift conference and learned that evidently Swift is expected to decay in about a year, which is sad. But hopefully some of these UVEX and other things will go up and provide a UV capability. But basically is TDEs in the optical and UV mainly present themselves as, in round numbers, 30,000 Kelvin black bodies. So if you really want to understand the energetics of TDEs, you kind of need the UV. The fact that they look like black bodies means they do not have the power law structure of an AGN. If you believe that the emission lines are due to recombination, there has to be an excess of hard UV over that black body. The black body itself is decaying too fast if you want to purely explain the broad lines by recombination. Anyway, so here's a typical light curve from one of our objects. So, the flatness here means that an awful lot of the flux is in the host galaxy. And then here's the UV dropping off. And this one has a significant X-ray image. And here from the review, there's just a whole bunch of light curves in temperature space. Some curious spectroscopic things. Since I want to talk about the optical, there's some things in the optical too. Well, the weirdness in the optical is that some of them show strong hydrogen, some of them show strong helium without hydrogen, and then some of them also show strong oxygen. So this would be 3 spectroscopic classes. But if we focus on UV, one characteristic is basically TDEs do not have magnesium-2 emission. Physically, the reason that might be interesting is that the presence of magnesium-2 in quasars was originally a bit of a mystery because it requires the existence of an extensive partially ionized zone. So that was eventually figured out. So models of quasars can produce magnesium-2, but it does suggest there's something physically different about the broadline regions of TDEs than quasars. The other interesting thing is that some of them show really, really strong nitrogen emission. In fact, they look like what are known as nitrogen-rich quasars. which are rare subclass, but also show super strong nitrogen emission. And an interesting way of trying to produce this is that if you do a TDE of a sufficiently massive star that the CNO cycle is active, the CNO cycle actually has built up a significant nitrogen excess in the core. And usually you never see that because it doesn't make it to the center before it gets turned to surface until it gets turned into something else. But here, if you take a main sequence star, which has run the CNO cycle for a while, you get to rip it open and expose the core before it does anything to the nitrogen. And so this may be an example, a probe of whether the star was a lower mass main sequence star or higher mass main sequence. The fun one are the repeating TDs, and I'll focus on ours, and object is 14K. So if you take a TDE of a giant star, you have a dense core, which has a very high binding energy, divided by an envelope, which has a much weaker binding energy. So if you go in, you are not going to rip apart the core before you rip apart the envelope, because the tides needed to do anything to the core are immensely higher than the tides needed to the envelope. And so with a giant or something with a more weakly bound surface layer, you can imagine going around multiple times, and each time you go around, you strip some of the mass of the envelope, and then the rest of it is held together by the gravity of the. So 14KO we flagged in 2014, not surprisingly, as originally as a supernova, but it had a weird continuum, and then was. Anna Payne came back later looking for repeating flares and realized that it had been kept repeating. And so as of the last paper, there were 21 flares. It's actually kept going. So there was a flare on schedule. See it? And here's an example of two flares that happen to be in test sectors. So here are the days. And notice this is on an absolute scale. These are not rescaled to look the same. And it goes up, rises rapidly in a couple of days, and it starts to die. Okay, well, you can fit these, and not often seen in the AGN literature, but you can go to the variable stars, and there's the O-C diagram. So the time predicted, observed time of whatever the peak compared to the predicted time of the peak. If nothing is going on, this is 0. If you have a period derivative, it's a parabola. And so here it is from July 2014 to July 2024 with the best fits. The period notionally is 114 plus or minus 0.5 days. Period derivative is what it says. The period is getting shorter by 0.2 days per orbit. And the notional lifetime is about 160 years. It's actually reassuring that it is not a perfect parabola. That the energy transfer you expect between the star and the orbit should not be an exact number. It should show some stochasticity. The simplest way to think about this is where you're going is you're going to put the energy into basically tidal modes of the star. And then depending on the structure of the star, when it comes back to paracenter, based on the phasing of the modes compared to the phasing of the orbit, you can get a slightly different energy transfer. So it would actually be worrying to me, at least, if this was a perfect parabola. It does have to come to an end. And we'll see that's a little bit long for me. But anyway, so here are a whole bunch of stacked flares going from this is X-ray column density, X-ray hardness ratio, X-ray flux, 2000 angstroms, and they're going through the Swift UV feature, UV bands out to V band. And it's 1, 2, 3, 4, 5, 6 flares stacked. And so the first thing you notice, they're all pretty similar. There's characteristic that just before the flare in the optical UV, the X-ray flux crashes, the hardness of the X-rays go up, and there is no obvious change in the color. Somehow the X-ray suddenly becomes significantly harder, but it's not due to absorption. Theory problem, anyone? And they are repeating an awful lot. There's one which really didn't match the peaks of the other. So there's one in 2021 where it peaked at only about half the peak of all of the others. One reason we like the TDE explanation, other than the main one we thought about, was a star basically penetrating through a disk, is that the even and odd peaks all look the same. There's no even odd dichotomy. Whereas if you imagine a star going through a disk, you'd sort of expect the alternating passages through the disk to look at least a little bit different. So that's sort of why we favor the TDE explanation. We can also get UV spectra. So here are a series of UV spectra going through it. No magnesium too, so another TDE-like thing. But if we just look at, say, the carbon-4 line, -4 days before peak to after peak, to then going into the next one, not quite into it. Just before the peak, carbon-4 is absorption with a bit of emission. Just after peak, the absorption is gone. You get a broad but not very strong line. You get stronger but narrower. And that seems to last almost until the next passage. So basically, you're seeing a rearrangement of an AGN broadline region in whatever, 2 weeks. Okay, enough about TDs. Ants and ents, it's not my fault. Anomalous nuclear transients and extreme nuclear transients. So stealing a Manti thing. Here's a space of time scale and peak absolute magnitude. And so here are kind of supernova, superluminous supernova, TDEs, and these things tend to sit here, more luminous but longer time scales than you see in TDEs. And these things sit way up here at even longer time scales and even longer luminosities. We won't go into the saga of 15. But if someone's really curious, they can ask about 15. The SEDs of these things can be black body-ish, but some of them are much more AGN power law-like. They last much longer. Okay. Their behavior, if you try to model them in terms of evolution, they kind of evolve somewhat more supernova-like, although no one thinks they're supernova-like. Anyway, their evolution doesn't really look quite as supernova. Anyway, here's one example, which is kind of fun. So again, you're getting just a flare. So it's not just normal and extreme of the normal AGN variability of these things. You get a much longer decline. This one was fun because there are extensive TESS observations in these bands. So there are the TESS-like curves. TESS was very friendly to us this time. It's usually quite hard to assemble something this coherent for this long a time from TESS. And so in that late phase, it's quite late now, this is way out here. Okay. It's varying like this over that period. And then at that much later phase, which is over here, the variability is basically gone. Okay, so I'd say, okay, I've shown you a bunch of AGN-like curves. That kind of looks like an AGN-like curve. All right, we've done all of this stuff. Let's model it as a damp random walk. And so here it is in someone else's version of the black hole mass and time scale. The black hole mass is from some work by Trachenbrot. And then this is the tau you get from that. And the time scale of variability is kind of in the right ballpark for what you would expect for normal AGN variability, which is interesting. They can also do other things. So some of these have basically absolutely no broadline regions. Here's the example of 20HX, basically featureless spectrum. TDEs vary in their spectra. As I said, some are dominated by helium, some by hydrogen, some have strong nitrogen, but none of them really are featureless. The other characteristic is many of these guys have the magnesium 2 emission. They don't really look spectroscopically the same stuff. The last one I talk about are changing look AGN. I should say this is the optical person's definition of a changing look AGN. X-ray people they have their own weird definition. It's not. So the basic picture is we have the dichotomy in AGN between the type 1 AGN showing broad lines, type 2 AGN showing only narrow lines. And then we have the unification models where in ground language, the idea is there's some obscuring torus of dust. If you are looking at it from above the torus, you will see the broad line region. If you're looking at it through the torus, you won't see the broad line region. In practice, it's not going to be a torus. The idea is you use obscuration to produce the difference between the two. There have been a lot of surveys for these. The biggest initial one was that the Sloan 4 project deliberately went back and took new spectra of a lot of previous Sloan quasars to look for changes in these spectral lines. You can do a big search for changing look things. And there are a bunch of other surveys. And so, in fact, the reference paper we use for Assassin is actually about a changing look quasar, NGC 2617. So here's its spectrum in 1994. Okay, you can see it's got no broad H beta, hints of a broad H alpha. And then when we came back to it, it looked like that. We can agree there are some broad lines. And then it's associated with a flare in the UV X-rays. And also use this to make one of the first continuum reverberation mapping. So the interesting question here, or at least an interesting question about this, is if I believe purely in the unification model, then this change in the look should be due to changes in the obscuration. And this object actually provided an interesting test of this because we also got a series of infrared spectra going through the event. So here are the optical spectra. Caltech. Actually, I should say, so when I was here, I had a friend who was going observing at Palomar and said, "Why don't you come along?" I said, "Sure." That's what pure theorists do. But this memo came down from on high, said that if the theorist goes to the mountain, he is to be neither fed nor housed. And so I took my brown bag up to Palomar and drove down at 3 in the morning or something. And I did, was a good citizen because on my way down there was someone with a flat tire who then got assistance at 3 in the morning. So that was my good deed for the day. The person who sent the memo, someone named. Anyway, so it goes down. Interesting is it's here, and what you can see is in 2006 SDSS spectrum, there's still some broad H alpha, but there's no broad H beta. Misty Bentz did a reverberation mapping campaign in 2014, focusing on H beta. And quite sure how they knew H beta was there. But anyway, when they did the reverberation mapping campaign on H beta, it had an H beta line, a broad H beta line. And then now it's even stronger. But the interesting thing is if you go through the infrared spectrum, where there's sort of a phase with no H beta, you can see as you go through here, you don't see any broad passion lines. It still has broad H alpha, but it has no broad passion lines. Okay. And then as the H beta comes back, the broad passion lines come back. If you could explain how to do this by rearranging dust, I'm open to suggestions, but it doesn't seem very promising. So to me, this seems a clear indication that a lot of these changing look quasars cannot be due to changes in obscuration. There are also other problems. It's very hard to rearrange fast. But this one doesn't depend on a theoretical argument. It's just that dust can't decide it will obscure the infrared and not H alpha. So that's a curious thing. Another really interesting changing look phenomenon is a changing look blazar. So to remind you, blazars are, quasars have jets, well, most of them do. In some cases, that jet is pointing almost directly at you. When that jet is pointing almost directly at you, the non-thermal emission in the jet can be Doppler boosted to dominate the observed luminosity. Okay, and so you get various classes of this. So a BL lac object is where the emission is so bright that you see no broad lines, which is sort of frustrating to the gamma ray people because they'd like to do these GZK cutoff things with blazars, and then they can't get the redshifts of them. So BL lacs is not much. 3C233 from the first is a blazar. technically it's a flat spectrum radiant quasar because it does have broad lines. Otherwise, the Greenstein and Schmidt paper would have been a lot shorter. But anyway, so it is a blazar where you can see the broad lines. Okay, so here's a particular source. I'm sorry, the scales on this plot from the paper, we should have worked on them more. But anyway, it underwent a big gamma ray flare. And so here it goes up in 2017. I'll just look at the peak. The peak here is 16th to 20th magnitude. And then suddenly here it jumps from 19th to 12th magnitude. And the gamma rays are at 10 to the minus 2, 1 something. So the gamma rays are down here. The gamma rays are up here around the purple. So in the optical, it brightened by about a factor of 3.5. So we've got a series of spectra going through this. So the numbering is in order, but the interesting thing is just look at it in terms of the absolute flux scale. So here it is in its brightest state. No emission lines. Let the flux drop, drop, drop. Start to see emission line, drops further. This one didn't get to H alpha, but not H beta side. As you get all the way down here, you can see sort of two broad lines. So it's really cute demonstration of the non-thermal emission creating the BO-LAC object by swamping the continuum line emission of the disk. When you ramp up the non-thermal emission, there's just so much brighter the lines, you can see them. Okay, that's what I was going to say. So we talked a little bit about normal quasar variability, that you can quantify various things. You can measure some numbers that are correlated with properties of the disk, like mass, accretion rate, luminosity, wavelength. With this problem that we then don't know how to really take them to the next step. How is that related more to the physics? We can measure accretion disk sizes in two ways. You generally find the wavelength scaling you expect for the temperature profile of a thin disk, but you generally find sizes which are bigger than you would expect. And some evidence that there is interesting variability in accretion disks beyond just these Lamb-Hosty models. As I said, we believe that this will become more apparent as you start looking for longer and longer light curves. These are its kind of subdominant years. They're only 1 year long and not 10 years. And then the other one was really just a bunch of tourism that AGN also vary for other things. You have the TDEs where something is off and turns on for a while, sometimes in a repeating way. You have these anomalous nuclear transients, which don't look like they're TDEs, but also are flares. It's changing look. And then I didn't talk about it because I was focusing on optical variability, but there are these super weird X-ray sources now. You get these extra short repeating X-ray flares, which those ones are mostly presently being interpreted as this star passing through. I'll stop there, and if you have any questions. So for the 14KO, it's the period of the star being disrupted. Yeah, sorry. Yeah, so that's why you need that steady disruption. Is that every time you go by paracenter, an elliptical orbit, every time you go by a paracenter, you get the peak in the tides. You strip a little bit of material, you go out again, and then you just keep doing that. But you lose energy from the orbit as you do that, and so you sort of expect a steady shrinking of the orbit. Or not in, so no, in the DRW model, we don't know what creates the damping. This is a phenomenological thing, is I can take this light curve, I can turn it into two numbers. Those numbers are correlated with various things. Want to know what our physics, we need a project. The timescales look different, their spectra look different. They show magnesium too. I'm just going to put on my Chris Stonick hat and say I'm just an observer. I, I, how about I am an observer when it is convenient? I really don't know. You know, it's you can worry about things is do quasars have disk instabilities? Usually, they certainly don't have the classic ones of straight binaries, but they seem sufficiently distinct. But if they turn out all to be TDEs, I'm not going to jump off a bridge. So it is a transient, which to our minds looks like a superluminous type 1 supernova. And there are various people who feel that. But I believe it is, but from my point of view, I believe it is still true that there is no clear TDE that has a spectrum that looks like it. Yeah. Yeah, it also got it's at one point I had an interesting discussion with someone by email that kind of actually said it boils down to. So you're saying is this tree looks different from all the other trees because it has a different bark. So it's a daffodil. Seems to be the gist of the argument. But yeah, I'm not sure there was radio data for that. Yeah. As far as I know, that one is still kind of unique. But if that one did it, there must be other ones. And it would be interesting to know what the radio did too. We're sort of expected to be at least more tracking the gamma rays than the discontinuum. Don't think we know. Yeah, no, just based on the radio is probably associated with jets. All I'm going on there. No, because like if dust is going to suppress the Paschen lines, it's got to suppress H alpha even more. Well, but if it's all driven by recombination, you've got to figure out how to have it. You have to have things with a combination where most of the H alpha comes from recombination in one region, most of the Paschen alpha comes from recombination in another region, but it's all cascades from kind of the same state. So it seems hard to arrange. Now, maybe it's possible, but that's was not immediately leaped to my mind how you can do it. As mentioned, it's there are also time scale problems. It's hard to rearrange the dust fast. because you sort of know how far away the dust has to be in order to survive. So you sort of have a time scale on which you can rearrange the dust. And that usually is kind of off some of these. So for Markarian 817, we actually do have data going all the way to K. And what appears to be the issue is you start getting such high amounts of smoothing from the fact that the disk is getting bigger that it becomes more and more difficult to get a signal out. So as you go to colder and colder dust, it just gets worse and worse. It would be an interesting experiment to try. Again, putting on my Kristonic hat is just because the theorist says you shouldn't see it. It's not obviously an experiment. But that one's going to be a hard one to get past. But it would be good to be able to do more than near IR. And the issue we're facing is that near IR data was, in a smart way of doing it, was done with one of these shell infrared spectrographs. So you really got all the way from K band to Z band. But it turns out a lot of the effects as you go out to K band start to seem to be subtle calibration, flux calibration issues that are making it hard to pull out some of the big problem. But yeah, I should say there are systems where you see dust reverberation. I didn't show an object here, but there are some which have been done by the CCF. Sorry, I'm blanking of the first author, but where you do see in Ys, you see a big Ys response later time. So that's right. I have not really thought about changing the emission spectrum. Thought about changing the temperature profile. I mean, obviously you can fix it by changing the temperature profile enough. But, of all the things about the thin disk, that kind of seems somewhat safe. Unless you want to really transport a lot of energy through this. The part of the problem is the thin disk is a simple model you can test against, kind of like Gaussian and non-Gaussian statistics. It's hard to decide what to test against other than the thin disk. But yeah, change the temperature profile. If you would sort of change the weighting. So Eagle and Dexter had an idea where the emission will be dominated by very large patchy temperature fluctuations. And you could use that to drive things outwards because the emission in the outwards parts was dominated by the up temperature fluctuations in the outer regions because you get a bigger bang for the buck by going up in temperature at a bit of a wavelength. You're on the blue side, and then goes down on the red side. That model probably has issues with other observations. That was a scheme to try to solve this problem, was to make the disk emission dominated by very large temperature fluctuations. Not, we're talking about 5 or 10%. Where they want more factors.